Welcome everyone to our video on Le Chatelier's principle. In this video, we are going to define the principle. We are going to explain how systems at equilibrium respond to three different stresses: changes in concentration, changes in temperature, and changes in pressure. Recall that we define chemical equilibrium as a state which is macroscopically static, as in the composition of the system does not change, but on the atomic molecular level, it is dynamic. The forward and reverse reactions are still occurring, but at the same rates. So how can we tell the difference between a system that is indeed at equilibrium versus a system that has just stopped occurring and is an incomplete reaction? The answer is that systems at equilibrium will respond in predictable qualitative and quantitative ways when they are disrupted. Le Chatelier's principle describes the qualitative way in which a system will respond when some sort of stress, concentration, temperature, or pressure changes are put upon a system at equilibrium. It states that when that external stress is imposed, the system will shift in a direction that will minimize that stress and restore a new equilibrium point. The final part of this is important. If we have a system at equilibrium and we impose some sort of change to that system or external stress, the system will shift the relative positions of the reactants and products, but it will eventually reach a new equilibrium point. So the system starts at equilibrium, it ends at equilibrium, but the equilibrium point has shifted. The first stress we will look at will be looking at what happens when we change the concentration. Changes in concentration only affect aqueous species or gases when we remove or add quantities of that chemical. Remember that pure solids and liquids do not vary in concentration, so adding more of those chemicals do not adjust any concentration changes, they just change the molar amounts, which is not the same thing. For changes in concentrations, let's consider this theoretical equilibrium system where the forward reaction is A and B combining to produce C and D, and the reverse reaction, moving from right to left, is chemicals C and D combining to form A and B. Let's take the system and assume it has already reached chemical equilibrium. Now let's think about what will happen if we increase the concentration of A. We know from chemical kinetics that increasing the concentration of some chemical will increase the rate of reaction. But since A is involved in the forward reaction, only the rate of the forward reaction will increase as a response to increasing the concentration of A. Since the rate of the forward reaction increases, this will consume more A and B, which will decrease their concentrations, and produce more C and D, which will increase their concentrations. The terms that we use to describe this is saying that the equilibrium is shifting to the right. It will shift until the right until a new equilibrium point is reached. Let's look at this same change again, specifically from a chemical kinetics point of view. At equilibrium, by definition, the rate of the forward reaction is equal to the rate of the reverse reaction. As we increase the concentration of A, that takes that equilibrium out of balance, and now the rate of the forward reaction is larger than the rate of the reverse reaction. But as more C and D are produced, their concentrations will increase. So that as the reaction proceeds, the difference in the rates will decrease because the rate of the reverse reaction will then begin increasing as more C and D are produced. And that will continue until the difference between the forward and the reverse rates reach an equilibrium point and the rates are once again the same. Let's now consider the opposite change where we decrease the concentration of A. Since now we've decreased the concentration of one of the reactants in the forward reaction, the rate of the forward reaction will decrease. So that means the rate of the reverse reaction is now relatively higher. As a result, there will be an increase in the concentrations of A and B and a decrease in the concentrations of C and D. So as a response to decreasing the concentration of A, which is on the left side of our equation, the system will shift to the left, producing more A and B, until a new equilibrium point is reached. And once again, we can consider these changes from a kinetics perspective. Whereas when we decrease the concentration of A, the rate of the reverse reaction is now much larger than the rate of the forward reaction. But as that reverse reaction starts to produce more in A and B, the difference between those forwards and reverse rates will become smaller until a new equilibrium point is reached where the forward reaction and the reverse reaction have equal rates. The second stress we want to consider is what happens when we change the temperature. Now, when we say we change the temperature, what we're referring to is setting the system at a new constant temperature. We cannot be continuously heating or cooling the system, because if we do that, then the system will never reach a new equilibrium point. To understand temperature changes, it's best to include the enthalpy change within the chemical reaction. If we view the forward reaction, we see that it is exothermic in that direction. As we move from left to right, energy is produced. The reaction is endothermic in the reverse reaction. As we move from right to left, the energy is consumed. If we increase the temperature that this system is at, the system is going to shift in a way to minimize the disruption. In this case, it will shift in the endothermic direction, so that it will consume the extra energy that was added to the system when we increase the temperature. In this case, it's going to shift to the left, or the reverse reaction will be favored. And if we consider the opposite change, if we decrease the temperature of the system now is going to shift in the exothermic direction. If we decrease temperature, the system's going to shift in the direction that will produce more heat energy. That will be the exothermic direction, and in this case, that will be in the forward direction. So the forward reaction is favored, or it will shift to the right, which is the exothermic direction. The final change we will consider is what happens when we change the pressure of a system at equilibrium. A pressure change is only going to impact the species that are in the gas state in this equilibrium system. Specifically, a pressure change is going to change the concentration of the gas species. When we increase the pressure on a system, that's going to be done so by reducing the volume. If the volume of a container decreases, then that's going to increase the concentration of the gas species, because there are going to be the same quantity of gas particles in a smaller volume. When we decrease the pressure, we can do so by increasing the volume. This will decrease the concentration of all gas species, because we are going to have the same quantity of gas particles in a larger volume. Let's consider that same nitrogen dioxide, dinitrogen tetroxide equilibrium system. If we were to increase the pressure on this system at equilibrium, that would immediately increase the concentration of all the gas species, both the nitrogen dioxide and the dinitrogen tetroxide, because we are going to have the same quantity of each chemical in a smaller volume. Since equilibrium has been disrupted, the system is going to shift in a direction that will minimize the stress. In this case, the stress is an increase in pressure, so the system is going to shift in a direction that is going to reduce the pressure. It can do so by shifting to the side of the reaction that has fewer gas particles. In this case, that's the right side, one particle versus two particles on the left-hand side. This reduces the pressure because gas pressure occurs from collisions between gas particles and the walls of the container. So that if there are fewer gas particles, there's going to be fewer collisions, and that will reduce the pressure. If we decrease the pressure on this same system at equilibrium, that will immediately decrease the concentration of all gas species. Decreasing the pressure will be caused by an increase in volume. So there will be the same number of gas particles in a larger volume, decreasing their concentrations. Equilibrium has now been disrupted, so the system's going to shift in a direction that will increase the pressure. It can do so by shifting to the direction that has more gas particles. In this case, that will be to the left. So the reverse reaction will be favored, and the system will shift to the left. That summarizes the three main changes that we can make to shift equilibrium systems. A question to think about going forward would be what would happen to a system at equilibrium if we added a catalyst. Can you explain what would happen using your understanding of chemical kinetics and how catalysts impact the kinetics of a chemical reaction?